Hello student, welcome to EPG Pathshala. I am Dr. Veil Pandian from All India Institute of Medical Sciences. Today I am going to talk to you about working with mass spectrometer, especially triple quadrupole tandem mass spectrometer. I'm going to tell you about the working and the other things done. This is for the paper of Molecular Techniques in Biophysics 1. In this module, you're going to see about how the experiments are being performed using LC-MS. What are the gas phase reactions happening in the formation of pseudo-molecular ions, rules which are applied behind the fragmentation process, and different modes of analysis. These are all the things we are going to say in today's talk.
There is lab of high precision bioanalytical laboratory. What you see here is the mass spectroscopy, which is triple quadrupole coupled with tandem mass spectroscopy. What you see here is the HPLC, which is the sample feeder, which tries to isolate the compounds, and this is a complete assembly of it. This is a pump, this is the sample feeder assembly, and this is a detector. And here it is getting separated. It goes to this machine. What you see here is, as I already explained you, this is a ESI, that is electrospray ionization probe, which is in which constantly the sample is being fed. Here this is the heater which tries to heat the gases which are coming inside, where the sample is getting nebulized. Here the charge mediated separation happens here, and it is they're focused towards this quadrupoles. Quadrupoles are kept in this range. First quadrupole is here, second quadrupole here, and third quadrupole is here, finally followed by the detector. What you see on the extreme left corner is the nitrogen generator, in which continuously from the atmospheric air, nitrogen is being continuously generated. And nitrogen is supplied at various positions here. What you see here is the turbo pump, which tries to create a very high dynamic vacuum. This vacuum is continuously going on, and there is another instrument that is kept here, which is the vacuum pump, which is giving a static vacuum. Together, it tries to maintain the condition which are essential for the traveling of ionized species inside this mass spectroscopy. Now let me just try to explain you how do we control and what type of information we get from this machine. How are we trying to analyze it? To be more precise, I'm going to now explain how this instrument is identifying this homotropy. Today we are going to spray homotropy to show you how this separation is taking place.
Application of mass spectrometry is classified into many categories. Few of them are: it is used for molecular weight determination, structural characterization of molecule, especially when you are trying to understand the structure of a molecule by doing the fragmentation analysis. Gas phase reactivity analysis is another important application. Qualitative and quantitative analysis of components in simple or complex matrices. This is considered to be as a LC-MS is considered to be as a gold standard for the analysis of compounds, especially in case of quantitation and understanding or analyzing the compounds which are present in matrices like blood, urine, sweat, or then the saliva, or in the biological fluids, or in the environmental samples. This mass spectrometry is highly helpful. Analysis of unknown compounds of importance, especially when you are trying to isolate a compound from plant in origin or from marine sources or from environmental sources. Analyzing the compounds, especially about their structure, it will be having a big role. Composition analysis during space missions. This is another one important application. I think I will talk about this later. And it's also having several other applications which are pretty diverse to comprehend. Gas phase reactions in mass spectrometry are very important to understand what's happening inside this instrument. Mass spectrometry is an important structure information tool for chemists, and it is increasingly becoming an important tool for those in biological sciences, including those who are working in drug discovery, environmental toxicology, proteomics, biomarker analysis, metabolism studies, and even the those who are working with newborn metabolism screening. Mass spectrometers are nothing more than a gas phase reactors in which unimolecular reactions or bimolecular reactions in which unimolecular fragmentation reactions of ionic species can be observed. So these reactions are explaining about the structural information, and the structural information is converted to a quantifiable analytical tool which is considered as a gold standard in the analysis. Let us try to understand ionization methods and the chemistry of gas phase reactions, as these reactions play a key role while ionizing a compound in the gas phase. So many of these ionization sources are electron impact ionization, chemical ionization like APCI, atmospheric pressure chemical ionization, atmospheric pressure photoionization, field desorption, fast atom bombardment, matrix assisted laser desorption ionization. In all these conditions, the reaction is happening in the gas phase. However, key physical organic data about these reactions which are happening in the gas phase, especially thermochemical reactions and the kinetics of these kind of reactions, are not often known. The post-source reactions, especially internal energy of ions, time taken between exit of ions from ionization source, and pressure of mass analyzer, they make a lot of difference, especially once if the molecule is getting ionized by the ionization source towards the detection. In between these two events, whatever is happening, it depends upon all these factors. Let's understand the thermochemistry and kinetics in gas phase, whatever we know as of now. As you know, enthalpy is when a process occurs at a constant pressure, the heat eval, either released or absorbed, is equal to the change in enthalpy. Adiabatic condition, when a gas is compressed under adiabatic conditions, its pressure increases and its temperature rises without the gain or loss of any heat. And we need these basic principles to understand this thermochemistry and kinetics in gas phase. Next important one is Bronsted Lowry theory. I think all of you must be familiar with this. A substance can function as an acid only in the presence of a base and vice versa. When an acidic substance loses a proton, it forms a base called the conjugated base of an acid. And when basic substance gains a proton. In this reaction, when hydrogen chloride, when it is combining with ammonia, it forms an ammonium ion with a negative chloride ion. So here uni or bimolecular reactions of a gas phase ions in ionization or inside the mass are governed by thermochemistry and kinetics. Let us try to understand what happens to the cations and anions. The ionization potential is classically defined as the energy required to remove an electron from a molecule or atom. In adiabatic, ionization potential is the lowest energy required to affect the removal of an electron from the molecule or atom, and corresponds to the transition from lowest electronic, vibrational and rotational of isolated molecule to its lowest electronic, vibrational, rotational levels of isolated ion. Basically, the difference is between a molecule or atom to isolated ion under the lowest vibration rotation energies. The enthalpy of formation of a neutral molecule is enthalpy formation of an ion which is having a charge. In the vertical IP is another one in which the energy change corresponding to an ionization reaction leading to the formation of the ion in a configuration which is the same as that of the equilibrium geometry to ground state neutral molecule. In this case, that in the ground state, what's happening is that a molecule is getting converted to its ion without any change in its equilibrium geometry. So here, in this kind of reactions, a Frank-Condon principle applies where vertical IP plays much more a predominant role than adiabatic IP. The proton affinity is a relationship between the enthalpy of the pseudomolecular ion, that is M plus H plus ion, and the molecule M. So this is being defined by these equations. Unlike adiabatic IP, with no enthalpy change, the proton affinity is defined as a function of temperature, whether at 25 degree centigrade. In case of anions, so far which we have seen about cations having positive charge. What happens in case of anions? Where a molecular deprotonation is a process occurs, where a molecule loses a proton and carries a minus charge. The anion proton affinity is defined as enthalpy change measures the ease of losing a proton from a molecule. This is related to the inherent acidity of a gas phase molecule at normal temperature. The electron affinity is a stable gas phase ions are formed after the loss of an electron depend upon the negative ion equivalent of ionization potential, which is represented by this formula. So electron affinities are represented as 0 Kelvin enthalpy change, and it is possible to have either vertical or adiabatic electron affinity. Chemical ionization process. This process is employed in atmospheric pressure chemical ionization, where corona needle is used for charge transfer. In the ionization mechanism of chemical ionization, it relies on electron impact ionization to some extent for the initial ionization event. When a source is added with chemical ionization gas like ammonia, that becomes ionized through charge transfer process through corona. This creates a reactive species that can ionize the analyte of interest. The ammonia, ammonia becomes quaternary charged ion, then it transfers the charge to the analyte, which is of our interest. That is how this atmospheric pressure chemical ionization process works. Atmospheric pressure photoionization. Like atmospheric pressure chemical ionization, we have another ionization method which is called as atmospheric pressure photoionization. Here the corona needle, which transfers the charge, is replaced with the ultraviolet light, and this ultraviolet light which is causing the ionization of compounds here. An analyte molecule M is ionized into a molecular ion provided that the ionization potential of the analyte molecule is below the proton energy. In the presence of protic solvents, the molecular ion formed by photoionization may extract a hydrogen atom from the solvent to form MH plus ion, that is pseudo molecular ion, by the addition of one proton. This happens in case of directly acting APPIs, where sometimes DuPonts are added to enhance this process, where the DuPonts like toluene or benzene, which first they undergo photoionization, and after that they become the source for formation of pseudomolecular ion later. So that's why that DuPonts are added in the solution to make this possible. Fragmentation process in which the mechanism involved has been explained by Bowie's rules. Fragmentation, when it is happening in the quadrupole 2, when the pseudo-molecular ions are colliding with neutral gas molecules, the weaker bonds are broken and the intermediates are getting formed. So, well, this is something which is very difficult to explain, but Bowie's rules, somehow it concludes about there are some general rules which are happening in that. In the anions, he found simple homolytic cleavage reactions where loss of a radical forms a stable radical anion is getting formed. Initial formation of anion neutral complex that could then undergo a variety of reactions, which could be deprotonization or elimination reactions. Intermolecular proton transfer can lead to a new deprotonated species which fragments via an anion neutral complex. Rearrangement reactions sometimes lead to internal nucleophilic substitution or displacement and skeletal rearrangement reactions. Sometimes it's very difficult to comprehend what type of reactions which are happening inside, because this is happening in an exotic condition which never happens on your lab, on your experimental table. Therefore, we could only explain that based upon the fragments which are getting formed. We try to explain what would have happened. This gives us much more a better understanding about what's happening inside the fragmentation process. Here, I'm trying to explain you by this pictorial representation the working principle of quadrupoles in mass spectrometer. As I already explained you, the source, in the gas phase, the ions are getting formed and that enters into the first quadrupole where it is getting separated, and after the separation it comes to quadrupole 2 where it behaves like a fragmented, where the neutral gas molecules like nitrogen or argon is accelerated to collude with the pseudomolecular ion. So here this causes fragmentation of the original ion, which gives rise to smaller fragments, what you see in the quadrupole 3. In the quadrupole 3, what we see here is it is just getting formed because all of them are getting fragmented completely. In this method, quadrupole 3 is kept at a full scan spectra. Basically, it will be running from all molecular weights to look forward for the fragments of its parent ion, which is coming through the quadrupole 1. I'm going to explain you different modes of analysis possible in the mass spectrometry. Here we have different analytical methods in which different quadrupoles, all 3 quadrupoles, are doing different functions. First of all, full scan mass spectroscopy, in which all 3 quadrupoles synchronize to scan all the molecules which are coming out of the solution where it is getting ionized into by the ionization source. So you monitor all of them. In the single ion monitoring, particularly you select the one which is of your interest and it is getting transmitted outside. This helps us for the analysis of compounds which cannot be fragmented and which are not suitable for MRM. This is a highly sensitive one, however it will be having high background noise. Third one is that MSMS product ion mode, in which this is the most helpful method before we design MRM, that is a particular method. However, this MSMS product ion mode helps us to understand or helps us to get the product ions or fragmentation pattern for structural elucidation studies. Here the quadrupole 1 allows a particular compound to go, quadrupole 2 does the fragmentation, and the fragmented ions are scanned for different molecular by quadrupole 3, where it gives us the information how the fragmentation has happened for that particular compound. This information is highly helpful to choose a transition which is selectively, which can monitor, which can be used in the next one, that is MRM. In MRM mode, multiple reaction monitoring, here one particular ion is selected and it's fragmented. Its particular fragment is selected by quadrupole 3. Therefore, you get a combination, what we call it as a transition. This allows us to pick up a compound with the highest degree of selectivity. So this is used for analytical purposes as a gold standard. There are several source dependent parameters, compound dependent parameters. Although these parameters, they differ between one instrument and another instrument, by and large almost all the instruments go through the same process. In the triple quadrupole mass spectrometry for quantification, and there are different modes as I told you, what for they are used. I'm just trying to tell you in brief. Full scan MS Q1 and Q3, which is used for qualitative scan. Single ion monitoring SIM is selective quantitative scan, as I told you, for compounds which are not capable of undergoing fragmentation. And this is very highly sensitive but having a lot of background noise. Full scan product ion for structural elucidation. Selected reaction monitoring or multiple reaction monitoring. This is for quantitative target analyte scan or analysis. Precursor ion analysis, again used for screening scan. Neutralizers, again used for screening scan, where when you are trying to analyze glycosides, where you have a glycon and a aglycon, and when sugars cannot be ionized, therefore their loss can be monitored. Or phospholipids or flavonoids, in all these cases neutral scan is a very important one. Data dependent MSMS scans or full scan MS scans, neutral loss precursor, all this together are put up together and an algorithm is made, and these algorithms are selectively used for finding out information about data. Is a very intelligent way of doing a structural elucidation or trying to find out an unknown compound when this algorithm is used to analyze compounds. Okay, as of now we have seen several parameters, we have seen gas phase transitions, we have seen different modes. Now let us see their applications, where it can be used. In this picture, what you see here is the quantification of compounds having biological origin and structural elucidation. So what you see here is a molecular and fragment ion spectrum of homocysteine thiolactone, which is coming at molecular weight of 118, where the molecule is 117. When it is getting protonated, it comes in 118. And the formation of all transitions, what you see here, and the structures which has been derived for that particular compound. When it is broken down into fragments, all what you are seeing here is 56, 72, 90 and 100 are different structures which are getting formed after the fragmentation. As I told you earlier, it is very difficult to explain how it is getting formed as it is happening in an exotic condition in the mass spectrometer. In the analytical modes of tandem mass spectroscopy, analysis of compounds using full scan spectra. What you are seeing here is a full scan spectra which is scanning it from 100 to 800 Daltons. So it's also Q1 scan, we call it as. By using RF and DC voltages, the M/Z ion trajectory is monitored from low to high. The ratios of ion transmitted related to the total window of ion is called as a duty cycle, which denotes transmission efficiency. This can be combined with the trap function to get high accuracy in mass analysis. This mode in which RF DC voltage is fixed to get a particular mass by charge ratio, that is a particular ion which is getting selected, used for SIM, that is single ion monitoring, as I already explained you. The scan what you are seeing here is monitored from 100 to 800 Daltons to see different types of peaks which are coming inside. What you see here is multiple reaction monitoring, or we call MRM, or selective reaction monitoring. Q1 does the SIM mode, that is a single ion monitoring. It sends it, and Q2 induces collision to make it to fragments, where Q3 selects a specific ion. In this combination of Q1 and Q3 gives a specificity for an analyte in bioanalytical analysis. Q1 and Q3 are decided using the knowledge about the bond broken during the process. This gives us high degree confirmation about the molecule what you are looking into. This mode is a gold standard for quantification of compounds as of now. The chances of having same molecular weight compounds having similar species in Q3 is remote. Moreover, you already got one-dimensional separation which is achieved by your column chromatography through HPLC. Here again second dimension is happening through Q1. Third dimension is happening through this combination of Q1 and Q2. Therefore, it is considered as a gold standard. In this picture, what you see is amlodipine, which is one of the antihypertensive drug, which is getting ionized and it is giving rise to the transitions of fragment 1 and fragment 2, in which the transition of Q1 by Q3 is 409.8 to 294 and 409.8 to 238. These two transitions. With this particular dual time, discrete collection of data for data point is achieved to create peak which can be quantified. Apart from the things which I told you earlier, analyzing structures and their charge state is also possible by using this instrument. What you see here is the ESI-MS spectrum showing the molecular ion fragmentation pattern of pralidoxim, which is a drug. And what you see here is that it shows that it's getting singly protonated, and from the molecular weight, it's already is a quaternary ammonium compound. Therefore, it's already charged one. So, therefore, it is not undergoing separate protonation. What you see here is, as such, its molecular weight is shown here. So, it's a molecular weight of this compound is 137, and you see here is 137, and it's getting formed. Single ion monitoring mode, SIM mode, is very important mode for finding out the substances which are not undergoing good fragmentation. It is the simplest qualitative experiment on mass analyzer, single ion recording on selected ion monitoring with a basic configuration. This system replaces UV visible spectra or refractive index or fluorescent detectors for HPLC for quantitative experiments. The compounds do not have weaker bonds to be broken during collisionally activated dissociation as bonds to be broken during collisional cadec. All the molecules are suitable for this SIM monitoring. Apart from classical multiple reaction monitoring or single ion monitoring in triple quadrupole type of instruments, there are several other modes of analysis can be carried out. For example, precursor ion scanning, in which sometimes we get a fragment ion uniform fragment ion which is coming from a species. I mean, for example, you take passepartout choline, where constantly, it will be having several type of combinations of fatty acids, but whenever you see in the when you just look forward for fragmentation, you will be constantly getting choline. With just holding the choline in the quadrupole tree, we try to look forward for the precursors of the ions. So these kind of experiments confirm what are all the molecules from where you're getting a constant fragment ion. Whenever we try to do subspecies analysis, where a commonality, when you try to look into it, the fragmentation pattern helps us to see similar species. Similarly, neutral loss or gaining, which can seen in the scanning mode, where fragmentation leading to the loss of neutral or loss or gain of loss of neutral or loss of gain. Qualitative information about this gives a complete qualitative information about the molecular structure. Time delayed fragmentation experiment is another type of experiment which we call it as the ms to the power n. This is used for a structural elucidation of a compound. This is subsequent fragmentation. You take a molecule, you just converted it to its protonated form or deprotonated form. You go for banging with neutral molecules. Along with time, slowly you do this experiment. Stage by stage, you will be able to see how the structure is getting collapsed, and this information gives us much of information about its structure when you try to resolve the structure of an unknown compound. This helps us to identify new molecules. So students, let us now summarize what we have learned in this today from today's module. We have seen about gas phase ionization reactions forming pseudomolecular ions, that is protonated, you could say anions and cations. Formation of cation and anion as a result of proton transfer, the mechanism behind it. Ionization in photoionization process, how the dew points are working, how this protonation is happening in the photoionization mode. Fragmentation, what types of fragmentation which has happened, and from using the fragments, what are the things which are possible to do. Modes of analysis and some of their applications we have seen.